The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, I guess we can get started here. So welcome. Today we're going to do Bayesian updating, which is to say we're going to be using Bayes' theorem to learn from data. We're going to update our beliefs about various hypotheses based on the data. For this week, we're going to have known priors. We're going to know our belief about the data ahead of time for certain. We'll draw coins out of drawers or pull things out of hats, things like that. Starting next week, and we discussed this a little last time, we'll have unknown priors, which is you'll have to be making up those priors, and we'll teach you techniques for making it up. So the first slide is just XKCD's view of Bayes' theorem. Let's go on. We want to start with a clicker question here. So the question is, which treatment would you choose if you needed a treatment? Treatment 1 cured 100% of the patients. Treatment 2 cured 95% in a trial, and treatment 3 cured 90%. So with this information, which would you choose?
With only this information.
With only this, if this is all I told you, which would you choose? I recognize that you might not be too happy with just this information, but if this is your best information, what would you choose? All right, there's some holdouts for the 95% cure. I'm not sure why. Really, that 95% was just, they cured one person 19 out of 20. They got them 19 out of 20 well, however you say that. Yeah. All right, so there's even a few more holdouts. All right, what if I gave you this information? Treatment 1 cured 3 out of 3 patients, that's 100%. Treatment 2 cured 19 out of 20 patients, that's 95%. Or you have a standard treatment which has cured 90,000 out of 100,000 patients, 90% in clinical practice. Now which one would you choose?
Oh, it's very interesting. Yeah, it totally changed.
What's that?
It totally shifted.
It totally should, really?
We have a bunch of very conservative people.
Right. So the majority would choose the third choice, 90 out of 100,000. I think, well, someone tell me, what's the intuition there?
Because it's been more tested.
It's been more tested. 3 out of 3 is 100%, but do you really believe 100%? Not yet. Maybe it'll prove out in time. 19 out of 20 is a little more, but for most people, for 79% of you, that's not enough. The 90 out of 100,000 seems like good odds, and it's well tested. 19 out of 20, if the next person tested doesn't get better, now you're back to 90%. So that doesn't seem like quite enough. What if it were 95 out of 100 patients? We'll let you click in there. Change number 2 to 95 out of 100, and let's see what people would do. Oh, you're very obliging. 95 out of 100.
Now it's about 50-50.
About 50-50.
Between 2 and 3.
Realistically, of course, what would you want to do? You'd want to do a little more of a research and find out what these trials were, how good experiments you thought they were, what people are thinking about it. But with just this data, that's what people would choose, and people would choose differently. OK.
Let's see. So now I'm going to give you a toy problem that actually mirrors the same kind of effect we saw on the last slide. So suppose in this MIT mug, I have dice of 2 types, 4-sided and 20-sided. All right? So I'm going to reach into the mug. I'm not going to look much. I'm going to randomly pull out a die. I'm going to roll it. All right, I got a 1. OK, I got a 1. Now, just based on this information, which type of die do you think I randomly chose? The four-sided. Someone want to give an explanation of why they think the four-sided is more likely? It's greater probability. What's the probability of getting a 1 on the four-sided die? And what about on the 20-sided? OK, so we see that it would be more likely to roll a 1 with a four-sided die than with a 20-sided die. So suppose I tell you that I really, in this cup, only have 1 die of each type. All right? So does that change your analysis of which die is most likely? Don't hit forward yet.
I wouldn't think of it. My hands are still.
Or do you want to stick with the same reasoning? All right. Let me show you what's actually in this cup.
Ouch.
Well, you can't see it yet. Let's go with document camera. OK, that was actually what I had in this cup. Now what? So does this change at all your analysis of which die you think I rolled and got a 1 with? What type of die, rather? Yeah. Yeah? Now what do you think is more likely? Four-sided or 20-sided? How many 20-sided dice? I think I got 20 20-sided die there. All right, so raise your hand if you like the four-sided die. Raise your hand if you like the 20-sided die. Great. So that reasoning that you're doing intuitively is something that we want to formalize this week and next week, using Bayes' theorem to do these calculations in a systematic way to evaluate hypotheses based on data. And these numbers of, for example, how many die I had of one type versus another, we can encode that information in what's called a prior. And we'll come to that today. And you should have seen in your reading this idea.
OK, so I'm going to work through an example to start with. We have 3 types of coins, type A, B, and C. However it happens, the probability of getting heads with type A is 0.5. That's a fair coin. Probability of getting heads with type B is 0.6. And of type C is 0.9. And here's a box. It contains 2 of the fair coins and 1 of each of the others. So 2 of type A, 1 of type B, and 1 of type C. Suppose I pick one at random and I get heads. So this was like John picking a die at random and getting a 1. I get heads. Here's the question. Before I flipped it, I have a prior belief in what the probability that the coin was of each type based on the number in my drawer. After flipping it, my belief changes. The probability will change based on the data I get. And so a question you could ask, what was learned by flipping the coin? What we want to teach you to do to answer these questions, we have a nice way of summarizing all of that at once in a table. So here the notation. We have this nice scripty A, or H. That's no good. H is our hypothesis. That is, you're of type A or B or C. We're going to make a conjecture on what we think the coin was. Before we do anything, we have a prior. So what's the probability of, how did I label this, that the coin was of type A? Where all you know is I pulled it out of the drawer. So what's the probability it's of type A here?
Let me go back and remind you what the drawer looks like. What is it?
0.5. 0.5, or I'll write it like this. 2 out of 4, which is 0.5. And what's the probability? I'll shorten this. We're just type B. Yeah, 1/4, or 0.25. And probability that we're of type C is 1/4, or 0.25. This was one of our simpler counting problems. In the table, you can see that's encoded in the line, in the column marked prior. Before we take any data, this is what we'd say. This is the sort of odds we'd give if we were going to bet on this. But now we have some data. So once we have data, we can get the likelihood. The likelihood is the probability of seeing the data given a hypothesis. I won't write this out. I'll just point at the slide. John has a – you were going to make your mouse bigger.
I was.
Oh, OK. So the likelihood column, we use this term when we were talking about maximum likelihood, is the probability of the data given the hypothesis. And this is typically easy, or often easy, to figure out. What's the probability of seeing heads? Our data was I flipped a heads if my coin is a 0.5 probability coin. So the probability of seeing heads given a type A coin is what, somebody? It's 0.5. This is particularly easy because that's what we told you. The probability of heads with a type A coin is 0.5. What about for B and C? 0.6 and 0.9. So there, right here is the likelihood column in the table. Now, how do we get the posterior? Bayes' theorem says the probability of H given D, which is what I want. I want to know, given this data, what do I believe the coin to be? What's its probability? Is the probability of D given H times the probability of H all over the probability of D. Well, notice this numerator right here. That's just our likelihood times our hypothesis, our prior belief in our hypothesis. And so what do we get? When I multiply the prior column by the likelihood column, I get this column in red. And I'll call that the unnormalized posterior. Why unnormalized? Because it doesn't sum to 1. How do I get it to sum to 1? There I have to divide by the probability of the data. And how do I get the probability of the data? That's called the, I see someone mouthing it, the law of total probability. And the law of total probability says you multiply for each hypothesis this value times this value and add them up, which is in fact just the sum of the red column. So there I've written it 0.625. And now how do I normalize? I just divide by all my values in my unnormalized column by that normalizing factor 0.625, and I get these, what I call the posterior. Let's say, well, now let's analyze it. So now what's your belief? Which coin is the most likely coin after seeing this data? Still A. But what's happened to the probability from our prior probability? It's dropped. Which one has gained probability? C. C. Does that make sense? If I flip a heads, which coin is the most likely to flip heads? C. So I've shifted it. Suppose I flipped heads 3 more times. What would you see in the probability as I kept updating?
Say again?
The probability of C would get bigger at the expense of the probabilities of the others. If I flipped heads 9 times in a row, I'd be very convinced that I had a type C coin. One last thing to note about this table. I put totals down here. What does this total of 1 represent in the first column? Emily? Yeah. When I sum up the total probabilities, they sum up to 1. Same with this last. That's a probability. This I could sum because they were probabilities. Why didn't I sum this column? Those are the likelihoods. And what's changing as I move down this column? What's changing is h. That's not a probability function. It doesn't sum to 1. There's no reason that the likelihoods have to sum to 1. And here you can see they clearly don't sum to 1. So I don't sum that. That's an important, maybe slightly subtle point, that the likelihood function is not a probability function. OK, any questions here?
All right. So let's go back to this document camera. Got my trusty platonic solids. So we're going to go through a series of board questions now, 3 board questions, which are going to allow you to practice making these tables and getting a sense for how to do Bayesian updating, how to iterate it, just how it works. And our toy problem is going to be involving these 5 platonic dice. You all have them, but let's not break them out today, because it'd be very noisy with the cameras, I think. We'll use our 4-sided. Here, I got big ones. We got our 4-sided, 8-sided, 6-sided, no 6-sided. No, I don't have a 6-sided. I have the wrong dice. Hold on. We got 20. We got 4. We got 12. We got 8. 10. What are you doing there? That's not platonic. OK. And 6. So now I'm actually going to take these. You can watch this. All right. This is empty cup. OK, they're in there, right? OK. How do we do this? How do we convince them?
You're choosing one at random?
Yeah. All right, choose it. Don't let anyone see. Hand it to me. OK. So I have this die. Don't look at the others. I'm going to start rolling it, all right, in the secret bin. Jerry, we can have a student come verify that I'm not making this up. You ready? OK, here we go. OK, what'd I get?
8.
8. All right. So which die is it so far? What do you think? Could it be 4, the 4-sided die? 6-sided? 8? 12? 20? What's most likely? All right. Come take a look at another one. Ready? Got a 1. It's the same die? It's the same die. It's the same die. All right. So now what? Well, how does this change? Anyone want to tell me, how would this now change from before what you believe to be? Does it change what you believe at all in any way? You still think it's the 8-sided. Does it make the 8-sided less likely, more likely relative to the others? More likely. Wonderful. See, you guys all sense this in your bones. It's great. This can be so easy for all of you. All right. We got to keep going until we figure out what this die is. You love to participate. Come on. Ready?
3.
3. Oh, man. All right. Ready?
12.
Ooh. Now what happened? It's a 12-sided die, but it could be the 20-sided die, right? All right, let me just do a few more. I'll tell you what I get. I get 1. I get 10. I get 10. I get 12. I get 3. I get 10. All right. Who wants to bet? What would you be willing to bet? Suppose I was willing to give you, like, I don't know, 10 to 1 odds that it's the 20-sided die. I mean, of course, maybe I know something, so I can see the die. Right? So what we want to be able to do is precisely answer that question. All right? And it's just through this Bayesian updating. It's not so hard, but organizing your work is really important. So, all right, it was the 12-sided after all. So you all did good. All right, so this is the first board question. All right, I want you to practice making the table Jerry showed you. Make one for if it were 13. Make one if I had rolled a 5 instead, or do the same question if I had rolled a 9. And in each case, compute the posterior probabilities of each of the 5 types of dice.
Yeah, right. So
Wait, it's for normalized. For normalized. Oh. They didn't sum up.
You knew it was a 20-sided die.
Yeah.
All right, what about if it's a 5?
Yeah.
But that's it. But you see how that captures it very nicely in a table. All of your intuition. You knew it was a.
and for the general case, we also have to do the general case.
Well, the general case, we would just multiply these things. But there's no point in doing that.
So right now you're doing the d equals 13 case?
Yeah. Or I guess
I
we
see.
can do the general case. So in general,
Oh, I'm sorry. You're not combining tables. This is your likelihood column here.
Yeah.
And then this is your unnormalized posterior column. Is it right? Or no, this is actually normalized.
This is for like if it were like any number, like if we wouldn't know what number it was. There's chances.
The likelihood.
Yeah.
Absolutely. So the likelihood doesn't depend on. Wait. What are you doing? Rolling a 5 or a 13?
Rolling a 13, right?
Right. So rolling a 13, for the likelihood, you're computing the probability of data that you saw, the 13,
Yeah.
given the hypothesis, say that it's the 4-sided die. So
Right.
if it's the 4-sided die, what's the probability you would roll a 13?
0.
Great. Same with this, this, and this. But what about here? If it's the 20-sided die, if that's your
Yeah.
hypothesis, what's the probability you'd roll a 13?
Oh, no, of 120.
Exactly. So that's the likelihood column. So this we're going to erase. Okay?
So then we multiply this by this to get that.
Exactly.
Normalize and we divide by 140.
Exactly. Exactly. Does that make sense?
Wait, we multiply these things
Multiply
over.
those two together
Yeah.
to get this unnormalized.
Yeah. Zero. And then what's the
And
next
then we
one?
divide by 1/100, so it's going to be a 0.
And then at the end, it's normalized, it's going to be 1.
This is normalized. It's
So yeah, so you get to
the
just
same thing, it's just normalized.
Oh, I meant HD.
no.
No,
Yeah, no, you're right.
Yeah, but
HD.
normalized
One thing I want to point out is
'Cause this is
instead of using a
probability.
comma, all right, this is conditional probability. So it's probability of d
Oh,
given h,
Oh, yeah.
like this. Okay?
Oh, which one?
There you go. So that's absolutely right, right? At the end,
Right,
we want to know
because this
how
is-
likely each die was given the data.
So this total is just P.
That's right. Which is 1/100. Great. So now do it again. Yeah, exactly. You don't need to even make a new table. Awesome.
So this column plot the probability, right? Because
Yeah.
you sum over all the different hypotheses. It's got it's a finite.
Yeah, for each hypothesis, you take each hypothesis times probability of the data given the hypothesis, which is the same as the probability of D and H,
Yes.
right?
Exactly.
So you're partitioning it up sort of
Exactly. 'Cause this
based on the
equals-
hypotheses.
'cause This equals that times probability D.
That's right. That's right.
D is confused. What is P of D?
Probability of the data. So,
Fine. It's
right, so a priori, you don't know which die it is, right?
Yeah.
But there's still a probability that getting a 13, right? And what is that probability? Well, first, we would have to, in this case, we could only pick the 20-sided die.
Yeah,
That has a 1/5 chance of happening. And then, given that we picked the 20-sided die,
Yeah.
we have to roll a 13, which is a 1/20th chance, which is exactly why
Yeah.
this sums to 1 in 100,
Yeah.
right? And then more generally, you have the law of total probability.
Yeah.
Great. So here, I think you should keep in mind which is the D and which is the H. Maybe write it above.
Okay.
Otherwise, it's a little confusing to know what. Great. Okay, and so these are the final probabilities you got if you rolled a 9. Is that right?
Yeah.
So there's something off here, right? Because
These are our priors, right?
Sorry, these are priors. I'm not labeling this. These are priors. This is going to be likelihood.
Tests. We got 2 tests. Like priors?
Wait.
so actually here I think you have likelihood.
Priors.
This is likelihood here. Exactly.
Wrong one. Okay.
That's likelihood. Your prior should be what?
0.2 for everyone.
Can't spell.
What should it be?
0.2 for each one.
Yeah, 1/5. Oh, I didn't see the points. Yeah. So that's your prior, 1/5 for each. This is your likelihood. Then you multiply them, and that's the unnormalized posterior, right? Let's have a brief discussion about it, and then we're going to give you something a little more challenging. So for rolling a 13, right, the first thing you do is ask, what is the prior? And you saw I had 5 dice. I shook it around. A student reached in randomly, not even me. So we can trust that it was 1/5 for each die, equally likely. That's a uniform prior, right? Discrete probability mass function. Great. Likelihood. Well, that's going to depend on the data, because it's the probability of the data given the hypotheses. The hypothesis in this case is how many sides on the die. So if the data is 13, what's the probability that I would roll that data, a 13, given that it was the 4-sided die? 0, right? It's impossible. Similarly for 6, 8, and 12 sides. But given that I had the 20-sided die, there would be a 1/20th probability of rolling a 13. That's the likelihood column. All right. The next column, what we call the unnormalized posterior, we multiply. Everything is 0, and then we get 1 out of 100 as the product for the 20-sided die. If we sum this up, by the law of total probability, we get the probability of the data. Now, a student asks, what does that mean? We don't know which die it was. Well, in this case, what it means is that it's reasonable to ask the question, well, if someone reaches in, grabs one of these 5 dice randomly, and rolls it, and gets, what's the probability that the result would be a 13, right? That's a reasonable question. And in this case, it's not so hard to analyze that directly, because the only way that could happen is if they picked a 20-sided die and then rolled a 13. Well, given that they picked the 20-sided die. Well, there's a 1/5 chance they picked the 20-sided die, and then a 1/20th chance they roll a 13 given that they picked the 20-sided die. So the probability of rolling a 13 overall is 1 in 100, the probability of the data. Okay?
Yeah, John, let me just say one thing. The way we would have done this before is you would have made a tree. The top branch of the tree would have gone to the 5 types of die, and then each of those die would have gone to all the possibilities. And the only branch that leads to a 13 is down to the 20-sided die and then down to the 13.
Notice also that this would be a very big tree, right? You have sort of 5 branches, and then this would have 4 and 6 and 8 and 12 and 20 coming off of it. Finally, we normalize. Using Bayes' rule, this gives us a posterior probability mass function. It's 0 for everything but the 20-sided hypothesis. Therefore, we get 100% belief, 100% probability, given that we rolled a 13, that it was the 20-sided die. Now, of course, you all knew that immediately. If you roll a 13, it has to be the 20-sided die. So let's look at a more interesting one that you did, the 5. So what changes? That's the big question. The only thing that changes is the likelihood. Granted, the rest changes, but everything, these 2 columns are computed from the first 2. The prior stays the same, okay? But the likelihood function changes because we have different data. In this case, if we roll a 5, we can't get that on the 4-sided die. We have a 1/6 chance on the 6-sided, 1/8 on the 8-sided, 1/12 on the 12-sided, and 1/20 on the 20-sided. Multiply those columns, get the unnormalized probability, or the unnormalized posterior. That sums to the probability of getting a 5. When you divide by it, it normalizes the posterior. And what do we see? Well, of course, you couldn't have used the 4-sided die. And of the remaining, the most likely, the most probable, given the data, is the 6-sided die. It has a probability, that hypothesis has a probability of about 40%, compared to the 20-sided die, which is only about 12%. OK? Last one. So this is the same deal. Again, the likelihood function is the changes. The prior is the same. We go through the table. The only two possibilities are the 12 and 20-sided. And the 12-sided, given that you rolled a 9, is about twice as likely as the 20-sided, which should fit with your intuition, right? OK, so next, we want you to not erase, but go back to the board you've already made. And we're going to explore a little bit the idea of repeated trials, right? Often, if you're collecting data, you don't just collect one data point. You collect a series of data points, maybe a series of patients in a clinical trial. You have data coming in, right? And you can update. You can update each time you get more data. And when you do this, your prior becomes a posterior on the first update. And then you use that posterior as the prior for the next update. Your beliefs are being updated as more data comes in. If you think about it, like when you walk outside this course, if you're like me, like you'll sort of suddenly realize you're doing this process all the time in your life, and you'll start approaching problems this way. And if you're really like me, you'll change your religion on Facebook to Bayesian. But you don't have to be that extreme. So great. So here what we want you to do is pretend that I rolled the die, and I got a 5. And then I rolled the same die. I didn't get a different one. I just rolled the same die, just like I did in that demonstration. And then I got a 9. OK? So now we have a sequence of 2 pieces of data, 5 and 9. So I want you to find the posterior that update in 2 steps. Then I'm doing this one. Yeah. I'm doing this one. OK. So let me show you how to do this. And then you'll do it. OK. So first we're going to update for the 5. Then we're going to update again for the 9. Magic. The prior, 1/5 for each, right? That's where we're starting from. We roll a 5. That's our likelihood. Again, you get a 0 for the 4-sided, and you get 1 over n for each of the other n-sided possibilities. We multiply. That gives us our unnormalized posterior for the first piece of data. Great. Now that is going to be our new prior. Now you may complain, wait a minute, this doesn't add to 1. But it's OK, because we're going to do it again. At the very end, we'll normalize. And we'll get the same answer as if we had normalized here and then normalized again, because we're just multiplying the whole column by the same scalar, by the same real number. OK? So it saves you work to not bother to normalize the first time. Great. So that's our new prior. We get our next piece of data, the 9. We have 0, 0, 0, 1/12th, and 1/20th as the likelihoods. We multiply this new prior by this likelihood, get the new unnormalized posterior. It only has 2 possible non-zero probabilities in it. The sum, the total probability of rolling a 5 and then a 9, is only 0.0019. OK?
That's using the unnormalized.
Ah, Jerry caught me. I was hoping a student would catch me. OK, maybe not. Maybe I was fooling myself. We haven't normalized. So it's not quite right. If we had normalized here, then by the time we got to here, we could interpret this as that total probability. But in any case, the point is we can normalize to get to the final stage, this final posterior, by dividing by the sum here. Now it adds to 1. And at the end of the day, what do we conclude? We conclude that it's almost 3 times more likely that it was the 12-sided die than that it was the 20-sided die, right? So this is very similar to what happened when I randomly had the 12-sided and rolled it. After 2 times, I had data that looked a lot like this. And if we had rigorously computed those probabilities, this is what we would have gotten. OK? So now it's your turn. So we want you to try the same thing, but in the other order. Suppose I first rolled a 9, and then I rolled a 5. So that's the first question. The second question is, can you do it in one go? Instead of doing it updating for the 9 and then for the 5, can you incorporate both the 9 and the 5 into a single likelihood function and do the updating in one step? All right, so try these and think about what's similar, what's different than what I just did.
You
don't have to. You don't have to. You could normalize it. Yeah. Then you would multiply by the likelihood. You'd get something again unnormalized, and then you'd have to normalize again, and then you get to your final answer. Or don't bother normalizing at this stage. Just multiply this by the likelihood, and then just only normalize once at the very end, and you'll get the same answer because, normalizing once and then normalizing again. It's the same as just normalizing at the very end. You're just multiplying a vector, this column, by a scalar, by rescaling it to make it unit length, and it's or unit, so the sum is 1. Exactly. Exactly.
Isn't number 1 going to be the same answer as the example we just did? Because we're going to be updating. I mean, this is going to be different. We just have to do it.
Absolutely. Yes, absolutely. All of these should give you the same answer because it's the same exact data, right? Starting from the same priors. But what we want you to really see is how the math proves that.
I mean, we're just multiplying different orders.
That's right. So it all comes down to what? What property of multiplication?
Associative?
That it's commutative.
Commutative. I guess you're also using associativity. It's just that multiplication is commutative, right? So it doesn't matter what order you multiply these columns in. The final result's going to be the same, right? So just think about how the order changes depending on the order of the 5 versus the 9, and also what happens if you think of both at once. How would you then make a table directly for that? Right?
So don't we just do like the...
So there should be a common
likelihood. Can we put the likelihood?
Yeah.
Well, just let's multiply the likelihood together.
So like the probability of D1 followed by D2, you just
I have to imagine a tree when I do this. I also have to imagine a tree when I do it because the tree is the best one.
5. I see. And so you multiplied, here, is this your likelihood? That's, you multiplied that. Where's your plus times this? By this? Oh, you even normalized. Yeah, you might, I see, right. So did you understand John's statement that you didn't actually have to normalize?
Right. But since you had already done it, we decided
no, I understand. It's a nicer number than 1 over 60. But if you didn't have it, you could have just used this column and normalized at the end. That makes sense? Excellent.
Thank you.
And I'm trying to...
This is just if you do it in one step, you just
I see.
multiply.
Did you get different answers?
No, it's not.
It's the same. Makes sense. You have the data. That's the evidence you have.
Yeah.
Right. So was this all clear? Was John's statement about not only needing the unnormalized posterior in the middle reasonably clear?
So what we were talking about is that if you were to use the normalized one, would then your unnormalized posterior be the actual probabilities? So like if you were to add them up, would it then
No, because in order to use the law of total probability, you have to multiply your likelihood by genuine probabilities. And the unnormalized posterior is not a genuine probability.
But if you use the normalized one.
If you use the normalized one, then it would be, this would be that would be the total probability of that. That's exactly right.
But in this case, it's this that's the total probability, right?
Yeah, this is now your posterior probability.
Yeah.
These are now the probability. So make a distinction. The total probability is about the data. And these probabilities here are about the hypotheses, right?
Sort of like the fit of the hypothesis to the data, is that?
You could think of that. They're genuine probabilities. This is the probability that you chose the 12-sided die given the data. That is, if I did this 1,000,000 times, and every time I rolled, I only looked at the times I rolled a 9 and then a 5, you would find this fraction of those times would be, it would be a 12-sided, and this fraction would be a 20-sided. So I forget what the numbers were, like 3 to 1.
Okay.
Yeah, makes sense? Excellent.
So we multiply them together, but then
You get the same exact answer, right?
so we get this answer.
That's okay, so it's unnormalized.
And then you normalize it, you get this,
Okay, so
right?
okay. There's no way to normalize it without.
This is
All right, let's come back together and take a look at what happened here. I saw some aha moments. That was great. Some people cited the commutative property of multiplication. That made me very happy. So what do? So when we do the 9 and then the 5, it looks just like what I did with the 5 and the 9, except the likelihood columns are flipped. So we have our prior. The likelihood for the 9 gives us this column. The product gives us a first unnormalized posterior. Then we do the likelihood for rolling a 5. The product of the unnormalized posterior and the second likelihood gives us our final unnormalized posterior. And notice the sum is still exactly what it was before, 0.0019. When we normalize, we get exactly the same answer that we had before. Now, if you contrast this with the table we looked at when we did the 5 and then the 9, what changed is these two columns were flipped around. And so I suppose this column was different and this column was different as a result. And then the final result, however, was exactly the same. Okay? Now, what if we do them both at once? What should that mean? If we do them both at once, then, well, we start from the same uniform prior. And our likelihood, now we should think of the data as both rolls, the 5 and the 9. Okay? Now, what's important here is that if we condition on a given hypothesis, for example, if we condition on the hypothesis that it's a 12-sided die, then the first roll and the second roll are independent events, right? It means that we can figure out the probability of a 5 and then a 9 on the 12-sided die. It's just the product of the probability of a 5 on a 12-sided die and the probability of a 9 on a 12-sided die. That's why we're justified in taking the product. If we condition on the die that it is, on the hypothesis, 12-sided, then the rolls are all independent of each other. In particular, we get 1/12 times 1/12 for rolling a 5 and then rolling a 9. And for the 20-sided die, we get 1/20 times 1/20. So now in one step, we update. Same exact sum. We normalize. Same exact answer. And I mentioned that some groups, maybe when slightly prompted by me, said, oh, multiplication is commutative. All right? That's all that's going on here. In the end, all we're doing is taking a prior, the first likelihood column, the second likelihood column, multiplying them together, and then normalizing it. Right? It doesn't matter what order those likelihood columns are in. It doesn't matter if we think of the 5 and the 9 and the 5, or the 5 and 9 multiplied together to make their own likelihood column. You get the same exact unnormalized result no matter what. Okay? So this is all there is to why it doesn't matter what order you update the data in sequentially. It just matters what the data is. Now, I also had a question. Why, if you could do it all at once, would you even bother with doing it once and then doing it again? Okay, it's a very good question. Does anyone want to suggest a reason, maybe other than the group that I talked to specifically about it? Yeah.
Well, I'm just thinking, as you're saying, if you have ongoing patients and you have to like continuously update, then like the first data set may be all that you have at that moment, but then you have to like keep.
That's exactly right. That's exactly right. So in life and in clinical trials, right, you don't get all the data necessarily at once. It sort of comes in continuously. You know, when I wake up in the morning, I don't know what temperature it is outside. I have a prior based on what temperature it was yesterday at about the same time. Like I have a memory of that. So that gives me some prior distribution on the temperature. Okay, that might be a continuous one, like maybe a bell curve. We're going to get to that next week, these continuous updating problems. Okay. And then when I get out of bed, I see that the window is covered in condensation. That's some data. I can update my beliefs. Probably means it's kind of cold. Great. Then I can open the window to let the cat out, and a burst of freezing cold air comes in like it did this morning. Well, actually, not this morning. This morning was great. Yesterday, it was cold. All right. And again, now I have more data, and I update my beliefs. All right. You can go through life this way. It'll give you a headache, but you can do it. Now, with clinical trials, the same thing can happen. Maybe you do a pilot study. Maybe you have some belief that eating almonds causes something, stomach cramps. Great. And maybe it's just for you. But you want to do a study about that. So maybe you know for yourself that eating almonds gives you stomach cramps. You're at the Harvard School of Public Health, and you really want to investigate this further. So you gather a few willing subjects, you feed them some almonds, you see if they get stomach cramps, how many of them, and maybe your prior ahead was you just kind of felt like you had this really strong belief that almonds cause stomach cramps because it does for you, and you really haven't asked a lot of other people. So you might have a lot of prior probability on that hypothesis being true. Once you collect a few more people, maybe you ask your friends, maybe you find that most of them don't have the same problem. Suddenly, your posterior belief changes, and now you're not quite so convinced that it's true. And then, if you're really ambitious and you have a lot of grant money from the NIH, you recruit 1,000 people, and you do a randomized controlled trial with placebo, and you find out that exactly 10% of the folks, complain about the stomach cramps with almonds, maybe 10% on the placebo also, so you're not quite sure what's going on. But the point is, you're getting data a little more, and you can keep incorporating it, updating your beliefs. All right, so that's the principle. One last thing I'll point out is, what if you have a prior belief that is so strong? Suppose you're so sure, for example, that almonds don't cause stomach pain, because it doesn't for you, and you're just sure that would be ridiculous, right? So you've put your prior probability at 0, right? How much evidence will it take? How much data will it take for you to be convinced? Infinite. No amount of data is going to convince you otherwise. This is why whenever you do this kind of Bayesian updating, it's generally best to leave a little bit of possibility for Santa Claus, OK? Like a little bit. Just so that should a fat white man come down your chimney and deliver the presents one year, you have the possibility to adjust, OK? So those are some things to keep in mind. I think we got one more board question that Jerry's gonna lead.
Right. So it's nice to get probabilities for hypotheses, but one thing you also want to do is predict what's going to come next. And so that's what we call probabilistic prediction. If I pick one of John's 5 die and I'm about to roll it, you could tell me using the law of total probability the probability that I get a 5. And we've done that. We did that in the first unit on probability in this class. But suppose he rolls a 5 first. Now I can update my probabilities for which die it is, which is going to update my estimation of the probability of rolling, say, a 4 on the next roll. So this is what we'll call probabilistic prediction. We can predict what's going to happen next, at least with probabilities, based on the data that we've seen. We update our predictions based on that. So here's a setup. D1 is the first roll, D2 is the second. I'll do this example. Oh no, this is a board question. You're going to do this. You're on your own here. So first, you don't know anything about the die except that one of the 5 was chosen at random. What's the probability that the first roll will be a 5? Now you've rolled that once. And you're going to roll again. And you can ask, well, now I've seen some data. I have some information about which die was chosen. What's the probability that I'll see a 4 on the next die? So that's your job to find that for this problem.
4, 6, 8.
Cool. All right, so this is your first answer?
Right. And then now we're just multiplying across. We get 0. 1 over 180. 1 over 220. 2000. Right? And then add those up. Right?
Yeah, get out your calculator. What are you dividing by to normalize?
Is this, I don't know. This is,
That's right. So this is when you add these up exactly the probability of the 5, right?
yeah.
So now if you want to repeat this process, you need to use your normalized posterior instead of the original prior.
That's what we're,
Yeah. Great. Now you just need to do division. That I can't help you with. Calculator.
Actually, do it.
Division skills.
I got it.
Either way.
Over 3,000.
dividing all those by that.
Yeah.
That's probably
So it's what?
no. Yeah, divided by 3,000 divided by 180.
56.
Now, is this the probability of 4 or the probability of 4 given 5? That's right. So let's see. So tell me what you did to get these.
So this column is probability of getting a hypothesis, which we calculated before, and then you sum it up to get the total probability of getting a 5.
Yep.
And then just to make the math easier, we normalized it, and then you took the new prior probabilities times the
Same likelihood.
Right.
Great.
And you get the new column, and then you add it up. And you calculate it. So answer.
Perfect. Now you said just for the heck of it you normalized it, but it's actually really important that you normalize it, because if you're going to use the law of total probability again, right, you got to be working with a probability mass function, something that adds to 1 here. If you didn't normalize, then your final answer get multiplied by something, right, whatever that normalization constant was, or its reciprocal. Perfect.
Okay.
Check these guys out.
And this right here is not a probability because it's unnormalized. So what should you normalize this by? Yeah. In other words, if you made a normalized probability here, it would be this divided by that, this divided by that.
So all we have to do is divide this.
Exactly right. Exactly right.
How's it going?
It's going fine. So we're just saying like
51 over 60.
5 is the sum of the
That's right.
and then
Point
math.
I know on the board it says
I'm just gonna add all these up.
0.085.
Now we have these two, so now we just
That's really small. I don't know what it is.
Okay.
We didn't do it.
So what did you get for this? How did you find it? So you summed up this, right?
Yeah.
Great. And then what did you do
We did the
next?
same thing for 4.
So
if you
starting from scratch,
you
or
started from scratch if you roll a 4.
okay. So how does that incorporate the fact that you first rolled a 5?
So we're trying to go back to the original Bayes, but that didn't work out so well because we don't know how to calculate this.
Exactly. All right. So this is no easier than that. So here's the idea. Here's the idea. So you start with this belief, right?
Yeah.
And you have your likelihood. You multiply them, law of total probability. You get the probability of rolling a 5. Right. Now at that point, after you've rolled this 5, your beliefs have changed based on that about the probability that you have each of the 5 dice. So if you take that and you use that as your prior here, then the likelihood, multiply and sum.
There we go.
That should give you.
I like that.
Okay.
Okay.
Oh, but now we have decimals. Okay, that's okay.
Now you have decimals. I can't, make your life too easy.
No. We're going to use these numbers. Here.
Right. So you multiply this number by this number by this. So in the end, you'll get all of these numbers except they're all multiplied divided by. So you should divide this by to get a probability.
Okay.
That makes sense?
Yeah.
So you have to be careful for figuring out probabilities of hypotheses. We could avoid using the unnormalized. We didn't have to keep normalizing. But when you want to do posterior prediction, you want real probabilities of data. So you're going to have to normalize these numbers at some point, either first or at the end.
Okay.
It's probably, if you're going to do it a lot, easier just to keep doing it.
Okay.
Okay.
So this one is not actually a one.
How are we doing?
You tell me.
You got the probability.
It's a beautiful use of color.
So we've got the probability, we took the posteriors, and we set that equal to our outlier, and then we're multiplying by the likelihood of getting.
So is this normalized or not normalized?
This is normalized.
Normalized. Good, because you want real probabilities there. Yes, thank you.
ones, and then we multiply by what are they likelihoods?
Yeah.
6 for each year, and then we probably each. Look at this. Look at this.
And now you're going to sum them up.
Yeah.
Right. That's perfect.
Way to go, Caitlin.
Because the law of total probability says multiply this by this. That's just what you did with the trees. Do you see it in the trees when I wave my hands? Yeah. Beautiful.
The probability of H is actually the probability of H and B combined. And then we get the long.
Like
Yeah.
our new prior is given
Yeah.
the data we have before.
Yeah. Okay. That's good.
You're adding them up? It's diligent. Okay, so that looks right. So let's think. How does this number compare to what you would have if you didn't know this other information? So suppose you knew nothing going in. Do you think that the fact that you rolled a 5 the first time makes it more or less likely that you roll a 4 the second time?
Actually less likely.
Is it less likely?
Because you get rid of the 4, the die that has only 4 sides.
So it might make it go down, right? On the other hand, you're going to give more probability to the 6-sided, let's say, than it had originally. So there's sort of competing forces. So I'm actually not sure. I'm not actually sure which is the right answer. But anyway, it's something you could easily check or compute. So
1, 2, 4 is what everyone's scheduled.
yeah.
This is a standard day. We always finish ahead of time. Oh, I don't need that right here. Okay, like with all the other answers today, we'll use the screens to show the table. So when we go through it, we do the usual thing we did before. We started with a 5, so we'll update our probabilities of the hypotheses based on that 5. So that's the first column is the prior, then the likelihood of getting a 5, which is 0 if you have the 4-sided die, 1/6, 1/8, 1/12, and 1/20. We get our unnormalized posterior, and then in this table, I actually got the normalized posterior, because when you're computing predictive probabilities, you need to use normalized probabilities. They should be true probabilities. So we used this column here of the posterior probability. There's different orders you could do this calculation. I think this is one of the straightforward ones. Then we look at the likelihood of D2 in the next column. Now I put a star for H4 because there's no way you could get a probability there if you have D1 and D2. If I had left off the D1, which most people did and which is okay because of the independence John talked about, given the hypothesis the rolls are independent, I would have had a 1/4 where I have the star, but I'm going to multiply it by 0 anyway. So who cares? So I have my new priors, my new likelihoods for the second bit of data, which are the same as the old ones, 1/6, 1/8, 1/12, 1/20. Now my total probability is done the same way. You multiply in this new language posterior 1, which is your prior for likelihood 2, times likelihood 2, and sum them up, and I get this last column. So again, once I have my posterior for the first bit of data, I can use that in the law of total probability to make a prediction. So what's happened right here? What's become more likely? Well, what's this 0.124 seems a little bit larger than I would have guessed ahead of time. What's happened with rolling a 5 and then a 4 to make that a little bit bigger? Any ideas?
When you roll a 5 first, it increases the probability that it's one of the lower dies.
Excellent.
So then it makes it more likely that you'll get a 4.
Excellent. That's what I would think too, that seeing a 5 and a 4, what did we roll first? A 5 makes the smaller die more likely. If the smaller die is more likely, then you're more likely to roll a 4 and a 5. For instance, if I had the 6-sided die, What's the probability I'd roll a 4 and a 5 with a 6-sided die? 1 in 36, which is about 3%. So this doesn't get up to 3%, but it's a little bigger than if I had the 20-sided die, where it would be, what's 1/400th?
Very small.
Small. John says it's small.
So this is one argument you can make, right? That rolling the 5 makes it likely that it's a smaller die, and therefore more likely to roll a 4 next. But is there another argument you could make for why maybe rolling the 5 would have the opposite effect? It might make it less likely to roll a 4 next.
My initial thought was, if you roll a 5, you know it's not the 4-sided die, and that's your die that you're most likely to roll a 4.
That's right. So I'm not as sure as you as to whether this goes up or down. I think there are two competing arguments. That on the one hand, it makes it more likely it's a 6 or 8-sided, but it also makes it completely impossible that it's a 4-sided.
I'll give you 3-to-1 odds that it goes
up.
up.
Oh, crap.
So what he doesn't know is whether I've computed it already or not.
He probably has. But he probably did it at like 3 a.m., so I don't trust it.
I simulated it in R.
I see. All right, are there any questions? That's what we have for today. So are there any questions about Bayesian updating or doing these computations? All right, great.